Welcome back to another video. Today we are going to prove that for every positive integer n, there exists a unique pair Tm such that n equal to the 2 to the f equal to the t times m, where t is an integer from 0, 1, 2, 3, and all the way and so on, and m is an odd number. Now, so what is this? You might start with plug in the number. You might start with 1, okay? So you have 2 to the 0 times 1. This means that you could have ordered pair 1, 1. So that 1 can be in this form. 2 to the 0 times 1. If you have number 2, you're going to have 2 to the 1 times 1. So you're going to have ordered pair. Sorry for the first one, the ordered pair turns out to be 0, 1. The next ordered pair is going to be 1, 1. If it's 3, it's going to be 2 to the 0 times 3. So it turns out to be 0 and 3. If it is 2, it turns out to be 2 to the 2 times 1. So you have ordered pair 2, 1. If it is 5, it turns out to be 2 to the 0 times 5, which is 0, 5. And what about number 6? 6 turns to be 2 times 3. That's what we know. So it turns out to be 2 to the 1 times 3, which is 2 to the 1 times 3, which is ordered pair 1, 3. Okay? 7 turns out to be 2 to the 1 times 7, so you have ordered pair 0, 7. 8 turns out to be 2 to the 3 times 1, so you gotta have 3, 1. 9 becomes 2 to the 0 and 9. Okay, so you have ordered pair 0, 9. And 10 turns out to be 2 to the 1 times 5, so you gotta have 1, 5. And what about 100? 100, for 100, okay, try to have 2 raised to the number. So you're gonna have 4 times 25. 25 is now odd, which is m. So it turns to be 2 square times 25. So we're gonna have ordered pair Tm, which is 2, 25. 200 is 8 times 25. So it turns to be 2 to the 3 times 25. So we have ordered pair Tm such that 200 equals 2 raised to the 3 times 25. And these ordered pair are uniques. Okay? So, what can we do? I want to use the principle of mathematical induction. So let's do this. So we're going to let P of n be this statement. 2 of Bn equal 2 to the t times m, where t can be integer from 0, 1, 2, 3, and all the way and so on to any integer that is positive, and m is an odd number. M is just an odd number. I want to use induction, so I want to start with the base step. So we're gonna have 1 base step. We start with n equal to 1, so we start from 1. 1 can be written as 2 raised to the 0 times 1. So this means that there exists a a unique pair. Okay, a unique pair 0, 1. Tm becomes 0, 1 such that 1 equal to the 0 times 1. Okay, hence P1 is true. Okay, P1 is true, so we have the base step. Let's go to next step. Next step is inductive step. So what is inductive step? For this one, I want to use strong induction, or the second principle of mathematical induction. So I gotta assume that P of K is true for any positive integer K, such that K less than Q. Since I just proved the base step in the case where n is 1, so I gotta try to write when Q is greater than or equal to 0, because I want to show the case where P2, P3, P4, P5, and all the way and so on, okay, to be true. And then I gotta show that P of Q is true. So we will start from Q. So Q is now Q is now an integer that is greater than 2. So I want to have two cases. So the first case is that Q is an odd number. Okay, Q an odd number. Okay, what can we do? Q an odd number. So we gotta have T equals 0, because Q is odd, so T must be 0, and M is Q, such that since Q is odd, so odd Q is going to be 2 times 0 raised to the 0 times Q. It's like I plug in M to be an odd number, and plug in T to be 0, so that 2 to the T becomes 1. So I gotta have odd number Q. So in this case, what does it mean by this? This means that when Q is odd, when Q is odd, what do we have? So there exists a unique pair Tm such that T is 0, M is Q. Okay, such that Q equal to 2 to the T times M. So if I have 1 is odd, we know that odd has only one form of 2 to the T times M. One form is that 2 to the 0 times 1. Okay, and 3 becomes 2 to the 0 times 3. There is no other T and M, so that 3 equal to 2 to the M. Okay, when Q is, let's say, 15. So how to have 2 raised to the power in order to have 15? Okay, this number right here must be odd number. that odd number must be 15. And 2 raised to the power of 2 or the exponent of 2 must be 0. Okay? 77 is an odd number. For odd number, it must not have 2 as a factor. So 2 raised to the 0 times 77. Okay? And there is no other form for this odd number. Got it? Now, let's go to another case. Another case is the case where Q is an even number. What about this case when Q is even number? For this case, I want to use the proof by uniqueness. Actually, it's a uniqueness proof. Okay? What does it mean? So there exists a unit X satisfying property Px. Okay? There is only one X unit X satisfying P. How to prove it? It is equivalent to, for all X, for all Y, satisfying property P. Okay? Property P. So you pick two elements satisfying property P here and try to show that X equals Y. Okay? So the two elements satisfying property P becomes the same. So this shows that this property P, so we've shown that we have uniqueness in this property. Okay? So we want to use uniqueness proof for this case when Q is even number. So now, since Q is even, what do we have? I gotta say that there exists. I gotta let L1 to be an odd number. Okay? L1 to be an odd number. Well, not necessary. I'm sorry. Not necessary. So L1 is just a positive integer such that Q is 2L1 and L1. When you factorize Q, when you factorize 2 from Q, right here, L1 must be less than Q, right? Okay, L1 must be less than Q. And when L1 is less than Q, it satisfies the assumption of inductive step. So, since L1 is less than Q, okay, PL is true. Okay, by the assumption of inductive step. Okay, so what do we have? We gotta have there exists a unique pair. Okay, TM, which is maybe T1 or M1, such that L1 is 2 to the T1 M1. And what is T1? Where T1 belong to this set 1, 2, 3 all the way and so on, and M1 is an odd integer. Okay, so Right now, we have, since q is even, we have L1 which is a positive integer such that q equal to 2L1 and L1 is less than q. Okay, so once L1 is less than q, there exists a unique pair Tm which is T1 M1 such that L1 equal to 2 raised to T1 M1. Okay, where T1 can be 0, 1, 2, 3 and all the way and so on, and M1 is an odd integer. Therefore, what do we have? So q becomes 2L1. So L1 is 2 to the Tm1. So we're gonna have 2 to the T plus T1 plus 1 M1. So we can write q as this form, as the form we want to write. And then, because I want to use the uniqueness proof, so I gotta have another integer satisfying q being even. Let's say I use, okay, since q is even, let's say I use L2. Okay, there exists positive integer L2 such that q becomes L2, okay, 2L2, and what is L2? L2 less than q. Okay, since there exists L2 less than q, what do we have? We're gonna have PL2 is true by the assumption of inductive step. Okay, why? Because L2 is less than Q, which satisfy, where is it? Which satisfy this assumption of inductive step. So we can write L2 as the term we want to write, right? So there exists a unique pair Tm such that T is T2, M is M2, such that L2 is 2 to the T is 2 raised to the T2 and times M2, where T2 belongs to this set 0, 1, 2, and all the way and so on, and M2 is an odd integer. Okay, M2 is an odd integer. So what do we have? So consequently, Q becomes 2L2, which is 2 times 2 to the T to the 2's M2, which is 2 raised to the 2 plus 1 M2. Okay, that's what we have. So we have Q, which is written as this term, and this Q can be written as this term. Therefore, what do we have? Therefore, we're gonna have 2 to the 1 plus to the T1 plus 1 times M1, which is Q, and Q is T to the 2 plus, is 2 raised to the T2 plus 1 M2. Alright? But since M is odd, M1, M2 are odd, okay? And 2 to the T1 plus 1 M1 equal 2 to the T2 plus 1 M2 are equal. What do we have? So we gonna have m1 equal m2, and then what next? 2 to the t1 plus 1 equal 2 to the t2 plus 1. Okay, so what do we have now? So we're gonna have m1 equal m2, and then t1 plus 1 equal to t2 plus 1. Okay, so t1 will be t2. Okay, t1 will be t2. So right now I've just shown you that if you have two ordered pair, t1 and m1, and another ordered pair, t2 m2, I've just shown that m1 equal to m2, t1 equal to t2. So I've just shown the uniqueness of this property. Okay, so by the proof of uniqueness. Okay, so there exists a unique pair Tm such that Q equal to the T times M, where T can be 0, 1, 2, 3, all the way and so on, and M is an odd integer. Okay, hence PQ is true. So once PQ is true, by the second principle, mathematical induction, we have proved that. So we have proved that Pn is true. Is true for every positive integer, and then that's what we have. This is the proof of example 1.2.6. Okay, so that's it for this video, and see you in the next video.